Adams State College. Great stories begin here.
All right, it's my pleasure to introduce our next speaker, Samantha Saville. She is actually, this is her second talk of the morning, so way to go. She's going to be presenting on a project that she did this summer as an RU, which is a research experience for undergrads. They have it in the science field, particularly for students who are at a smaller institution, and it's an opportunity for them to get experience at a large research school. She did also present this project at the National American Chemical Society meeting as a poster just about a week and a half ago. And so she's had some great, I think, exposure to giving presentations and getting this work out there. So I'll let her tell you about her project.
Thank you, Dr. Beaton. Last summer, I did a research experience at New Mexico Tech University, working with Dr. Corey LeClaire and with Annie Boyd-Latour from Otterbein University in Ohio, which is why she's not here. And we focused on catalysts that converted ethanol into hydrogen for fuel cells in a more cost-effective way. So the importance of hydrogen is it does several different things. It produces fertilizers and ammonias, liquid fuels, and is a great future fuel source. There are two ways of making hydrogen. The first is steam reforming, which is 95% of industrial use. But this is not a very good reaction because it happens in the vapor phase at about 800 degrees Celsius. So it's very dangerous, very cost ineffective. And it's a two-step reaction, the second step being the water-gas shift. And this is a general reaction of the desired product. So we take an oxygenated hydrocarbon, water, and that's supposed to go to carbon monoxide and hydrogen. That's the first step. The second way in producing hydrogen is aqueous phase reforming, which is what we did. And it has the water-gas shift in simultaneously with the first reaction. So on the previous slide was the first reaction. This is a water-gas shift reaction. It takes that carbon monoxide and water and turns it into carbon dioxide and more hydrogen. This happens in the liquid phase, so it's much safer and much more energy efficient. As you can see, this yellow line is the water-gas shift line. These first sets of black lines coming down are the aqueous phase reforming reactions, whereas these are the steam reforming reactions. As you can see, it happens about 400 degrees Kelvin. Subtract off, 200 and some odd degrees from that, gives you around your 200 degrees Celsius. And this happens at about 700, again, subtracting 200 degrees-ish. So the importance of ethanol is it's not toxic, it's very stable, so it's easily storable. It's easily produced. We actually are legislated to produce certain amounts of ethanol a year. And it's very reusable, which is one thing we actually looked at in our project because we got a lot of ethanol back from our sample, so we were thinking about reusing our ethanol because of its stability. So this is a general reaction of what we tried to do. We took our oxygenated hydrocarbon and water, converted that to carbon monoxide and hydrogen. Then, if designed correctly, in the aqueous phase reforming reaction, we can convert that carbon monoxide to carbon dioxide, which is a less hazardous greenhouse gas than carbon monoxide, and more hydrogen, increasing our hydrogen yield. With steam reforming, however, it can produce a lot of unfavorable reactions, this being one of them. It can, instead of taking that carbon monoxide and hydrogen and either leaving it like that or producing more hydrogen, it can actually take it and produce methane, which is very hazardous greenhouse gas and what we're having the biggest problem with for the greenhouse effect. So catalysts. A catalyst is something that directs and speeds up reaction. 90% of industrial processes use these. And when we picked our catalyst, we wanted it to do a couple things. We want it to maximize carbon-carbon bond breaking. This speeds up the reaction. And group 8 metals are the best at this. Platinum, nickel, so on and so forth. And we also, when picking our metal, we want it to be able to favorably perform the water-gas shift and to be able to have a small metal particle size on our support. And we want our support to have a large surface area to increase conversion area. So a support is a ceramic surface for a metal to bind to where the reaction can take place. This is a scanning electron micrograph of our support. These triangular pieces are our nickel, and all the gray is the support. As you can see from the scale right there, it is less than 1 micrometer, which that's 1/100th of a single hair on your head. So it's really, really small. So that's good. We want it to be small. Our methods of creating this catalyst, we did the combustion support method, which is where we take a fuel, which we use glycerin, and a support, we used alumina, put in a beaker, cranked it to 400 degrees Celsius, waited till it combusted. That drove all of our particle size to be nanoparticles, and our support conversion surface and our support surface to increase. From this point, there's only one way to attach the metal, which is the wet impregnation technique, and that is where you anneal the support, you add your metal, and then you anneal it again. And annealing is the process where we put the sample in the oven, heating it to extreme temperatures, reducing the sample by taking off excess carbon. So this is the old technique. We're getting away from that. We actually pioneered this new technique called combustion synthesis, and that's where when you make your support, you add your glycerin, your support, and your metal in the beaker, crank it again, combust it. There the metal and the support drives all the particles down really small, attaching it to the surface, and there's only one annealing process. So it's faster. We then reduce it by annealing it. We run a 10 weight % ethanol solution through our catalyst at 175 degrees to 400 degrees Celsius at about 100 psi's, 180 psi's. So this is our catalyst. These are the catalysts we focused on. The bolded words during and after. After means the wet impregnation technique, so we added the metal after we made the support. During is our new combustion synthesis technique. As you can see, sample C is only a 2 weight %, where the rest are 10. That is because the cost of platinum, which we're moving away from. So as only a summer research project, we can't really afford 10 weight % of nickel, so we used 2 and compared them per active site. So that is particles on the support that actively convert the ethanol to hydrogen. Sample A and B were designed to compare the old and new technique, and sample D was to compare the supports. However, there's only so many weeks in the summer, so sample D, there was no conclusive data on it because we just ran out of time. Our 10 weight % ethanol solution is housed in these 2 pumps that run through, I don't know if you can see it, these wires into our furnace housing reactor tubes with our catalyst sandwiched between 2 things of quartz wool. The ethanol runs through that at very high pressures and collects in these condenser tubes. From there, every 2 hours, we let this run to reach steady state. So after 2 hours, the gas is analyzed through this gas chromatograph, whereas the liquid from the condenser is collected, stored, and run when there's plenty of samples to run through this gas chromatograph. One is a liquid, one is a gas chromatograph. I know it's confusing. So gas chromatograph was our main source of analysis during our summer, and it uses boiling points to separate out chemicals. So this is a hydrogen peak, and this is a hydrogen peak from our raw data that we see when that gas chromatograph runs. We get more peaks on the liquid gas chromatographs, but as you can see, this hydrogen peak, much higher than this one, but it is misleading because we analyze this further and this isn't always as high as it looks. So this is our hydrogen yield comparing sample A and sample B, sample A being in blue, sample B being in the maroonish, I guess. And as you can see, sample B maxed out about 300 degrees Celsius, and sample A increased all the way, which is very promising. This is compared per active site, not per gram, because most of the nickel didn't stay on the surface of our support, it actually went into the bulk of it. So that was not a good thing. But per active site, sample A highly outperformed sample B, especially at lower temperatures, which is ideal for industrial use. This is comparing sample A and sample C, A again being in the blue. As you can see, sample C maxes out at the 350 range, whereas sample A skyrockets the whole way, and again, really focusing on the lower temperatures. Temperature program reduction, or TPR, was a qualitative analysis technique that we used to reduce our metals, to see how it reacted with hydrogen, and to test our metal and support interactions. Pulse chemisorption, another tool we used. This gave us our number of active sites, so this was very important for our analyzing our metals. It also gave us the metal particle size and how the particles absorb the hydrogen. The top graph is our TPR, and sample B is in red with a very strong 1 nickel peak, which is very good. Sample A is in the blue, and it has 2 peaks, the first being our support peak, the second being our smaller nickel peak. This shows that our sample A is unstable, which isn't good. And down here is our pulse chem data. As you can see, as sample A is used in the blue, its dispersion, surface area, and particle diameter all get better. Whereas sample B does the opposite, it actually gets worse. So this shows that both are a bit unstable, which isn't ideal, but the more we use sample A, the better it turns out to be, which looks promising. This is the pulse chem data for sample A, B, and C. Sample C having the best dispersion, not quite the best, well, the best surface area, and the best particle diameter, proving that sample C is the best catalyst to use. We already knew that, we're trying to find a better one. X-ray diffraction was my favorite tool we used, and it gave us our particle size, the phase of our particle, and the angles and intensity of diffraction. So this was good to know, to see what phase our catalyst was actually in. So this is a sample, the XRD data for sample A and A used being on top, sample A being on the bottom. Sample A has the 100% peaks for nickel aluminate, nickel, and nickel oxide. And the 100% peaks is, if this peak exists, that chemical or that compound phase will exist 100% of the time. So sample A used, all the nickel got reduced to nickel oxide, and so proving again that it is unstable. This is sample B, used on top, new on bottom. Sample B has the 100% peaks for the nickel aluminate and nickel. Notice the nickel oxide peak is missing, that is a good sign. We don't want nickel to oxidize. And the nickel peak stayed strong, which is another good sign, whereas the sport got rid of the nickel, which that's okay too. This is sample C, used on top, new on bottom. They both had very strong platinum peaks, and the used had a support peak. So to wrap up this presentation, we saw in the TPR, pulse chem, and XRD data that sample A and B are unstable, which is not good. On the last day of our research, our professor came to us and told us we'd been doing it wrong, actually. So the reason why these are unstable is potentially due to us reducing it at too high of a temperature. So we're disrupting, what they want to be too much, hence why they're unstable. And sample A does have less active sites, which again is not a good thing. therefore having less dispersion. But that could be due, well, that is due to it going into the bulk of the sample and not staying on the surface. And sample A and B, or sample A outperforms sample B and C, which is good, especially at lower temperatures, which is ideal for industrial use. If there had been more days in the summer, we would have really liked to reuse our ethanol to compare it to the new ethanol, and just see how well it converts if it's been used. And we'd really like to increase the weight percent of the nickel in our sample A to see if we could compare it on a per gram level to a sample B, which was the equal technique. I'd like to thank everybody I worked with, the National Science Foundation and the Department of Energy for funding my project. And are there any questions?
Adams State College. Great stories begin here.